Hello everyone, welcome to the session for quick revision of fluid mechanics. We will continue with the properties of fluids. And the next property of fluids is kinematic viscosity, which is denoted by mu. It is the ratio of dynamic viscosity to the density of the fluid. So the kinematic viscosity is equals to dynamic viscosity divided by density. But don't confuse with this ratio, and in few cases we'll confuse with like rho divided by mu. That means you will confuse with whether rho is in the denominator or the numerator. Don't confuse that. Here you can have a shortcut. Here kinematic viscosity is nu, dynamic viscosity is mu. So these rhymes like a same one, right? So for the mu will be the in numerator and the rho will be in the denominator. And coming to the units, and for the dynamic viscosity it is kg per meter second. For the density it is kg per meter cube. And if you simplify this, you are going to get meter square per second. Coming to the CGS units, we simply call Stoke. For kinematic viscosity, the CGS units are Stoke, but 1 Stoke is equals to 1 centimeter square per second, which we got this from here. Okay, converting this SI unit to CGS unit. And now 1 meter square per second is equals to 1 meter equals to 100 centimeters. You have a square here, just keep here, and it is 1 second. That equals to 10 to the power of 4 centimeter square by 1 second. So if you simplify this, you are going to get 1 meter square per second is equals to 10 to the power of 4 centimeter square per second. So now from finally what you're going to get is 1 meter square per second is equals to 10 to the power of 4 centimeter square per second. That equals to 10 to the power of 4 Stokes. Here centimeter square per second is equals to Stokes. So now finally 1 meter square per second is equals to 10 to the power of 4 Stokes. This is very important to solve your problems for any competitive exams. And now 1 Stoke is equals to, see, if you want to write for 1 Stoke, then this is your formula, which is 1 Stoke is equals to 10 to the power of minus 4 meter square per second. And in the problems, if they give like what is the unit for 2 Stokes in meter square per second, then you just, for a given Stokes, you just divide that with respect to 10 to the power of 4. 2 Stokes divided by 10 to the power of 4. Then it will be converted into meter square per second. Okay, that means if they gave the units in the Stokes, if you want to convert that into meter square per second, just divide that into 10 to the power of 4. And the next unit is 1 centistoke is equals to 1 by 100 stoke. Centi means 1 by 100 stoke is equals to 10 to the power of minus 6 meter square per second. Why it is meter 10 to the power of minus 6? Here already 2 is there, here 4 is there. If you add that, you are going to get 10 to the power of minus 6 meter square per second. And for this, the dimension units L square T to the power of minus 1. That means you can see here meters L square is there and the second T minus is there. Okay. And now we'll see the shear stress versus deformation rate for different fluids. Here in this subject we have two different fluids from the Newton's law of viscosity, which is like Newtonian fluids and the non-Newtonian fluids. We already discussed about this, right? So once again we'll see this. Fluid which obeys Newton's law of viscosity, those fluids are Newtonian fluids. And the fluids which does not obey the Newton's law, and those are non-Newtonian fluids. And coming to the Newtonian fluids, tau is equals to mu du by dy, where mu equals to dynamic viscosity, du by dy is velocity gradient or rate of shear strain or deformation rate. And the next, mu equals to tau divided by velocity gradient, right? Shear stress divided by velocity gradient. Here the mu is constant and it varies linearly. That means if you draw a graph like tau and du by dy here, you will get a graph like a linear one. Okay, so the mu or the slope, okay, here the slope is varying linearly. So for for Newtonian fluids, the mu is linear. That means it varies linearly. For Newtonian fluids, we have few examples like water, air, mercury, and kerosene. And coming to the non-Newtonian fluids, and these are which does not obey the Newton's law. And so here we have a Newton's law, which is tau is equals to mu du by dy, but it is not obeying that, so that's why it is not equals to mu du by dy. But it follows a power law model, which is tau equals to m into du by dy into n. Here m and n are constants. Okay, and now, or else you can call this as Oswald the Valley model. That means tau is equals to m into du by dy to the power of n minus 1 into du by dy. See, if you simplify this only, you are going to get this one. Okay, these both are equal, but in some textbooks they are giving like power law model. In some textbooks it is given by Oswald the Valley model. And now you can simplify this. See, if you get a common to the outside, then what you are going to get du by dy to the power of minus 1, and this minus 1 and these one get cancelled. Finally what you are going to get mu du by dy to the power of n, right? And now we'll see what is this m and n. M is consistency index and n is flow index. Consistency index and the flow index, and depending on this flow index the fluids will differ. We'll see that later. From Oswald the Valley model, mu A, which is apparent viscosity, we'll see what is this apparent viscosity, equals to tau by du by dy, which is shear stress divided by velocity gradient, that equals to m, which we already got from this Oswald the model, m into du by dy n minus 1, and here we have again du by dy, and that we got this to the left side. And now here viscosity mu not constant, right? And this is not constant, it is varying, so it varies non-linearly. That means if you draw a graph between like tau and du by dy, which is velocity gradient, you are not going to get the linear one. Okay, you're going to get some non-linear or any other curves. Okay, how you're going to get that for different fluids we'll see later. And now therefore such non-linear viscosity is called when the mu or the viscosity is varying non-linearly, and that viscosity we call apparent viscosity or effective viscosity. And if n equals to 1, m equals to mu, the power law model equals to the Newton's law of viscosity. In this formula, if you keep m as mu and this n equals to 1, then the total concept or the total formula will changes to Newton's law of viscosity. And the next note here we have to remember is, for Bingham plastics and the Herschel-Buckley fluids, the power law changes to tau is equals to tau y, which is yield shear stress, plus m into du by dy to the power of n. Actual power law is, if you neglect this, and this one stands for the power law, but if you add this shear stress, which is yield shear stress, then that is useful for your Bingham plastics and the Herschel-Buckley fluids. If you want to show this Herschel-Buckley and Bingham plastic, you have to use this particular equation. Okay, and here for the non-Newtonian fluids, your mu varies non-linearly. And now these Newtonian fluids will be divided into two parts, which is like time independent and the time dependent fluids. And for the time independent fluids, we have pseudoplastics, and these are shear thinning. These pseudoplastics are shear thinning. The best example is your paint. Okay, when you're shearing that paint, it will turns to a thin one. That means for first, if you look the paint, it will be like a thick one, but as you brush it or as you sheared on a wall, it will be a thin. It will turns to a thin layer. And coming and this flow index, which is n, will be less than 1. And coming to the dilatant fluids, these are shear thickening fluids. Shear thickening fluids. The best example for this is your starch. So the first, when you keep some starch in your water, it will be like a thin one, but if you goes on stir it, the shear will increases the thickening of the fluid. So That means as we shear the fluid, the thickness of your fluid or the starch will increases. Here the flow index will be greater than 1. And coming to the next time independent non-Newtonian fluids, it is a Bingham plastics, where your flow index is equals to 1. And next, coming to this time dependent, these are thesiotropics fluids and these are rheopectic fluids. We'll see what are these fluids in the next coming session. Okay, we'll continue in the next session. Thank you.